Well, yeah, thanks everybody for joining. Like Egan said, my name is Chris Davidson. I work as an application engineer out of the Seattle area. And today we're going to be going through how you can hook up basically atoms and Nastran to create a flexible body representation of parts inside of Atom's view and Atom's car. This is the agenda really for today. First, an introduction on kind of three products: Atom's Flex, Atom's Durability, and ViewFlex, although the main coverage for today will be over Atom's Flex. We'll also take a look at a case study or two, and we'll talk about this modal representation, which is what Flexbodies use and how many modes you think you might need to carry. And then I'll go through a demonstration problem of hooking up atoms with Nastran through Patran. And then hopefully you'll have time to talk a little bit about damping and some more kind of advanced things like modal forces and preloaded bodies. And hopefully we'll have time to also do a short ViewFlex example, which I'll explain that in a moment. And then we'll have a summary and a Q&A session. Now this presentation that I'm giving today is available to you. Nejan can send it to you. And the presentation covers a lot more detail than what I'm going through today. We just don't have enough time in today's session to really go through some more advanced things for advanced users, basic theory, and so forth. So if you want more in-depth knowledge, just send an email to Eugen and request this PowerPoint. And then also that you can get the model, the demo model that I'll be using as well. Okay? So first of all, what is a flexible body? Well, for people who haven't done this before, a flex body is a type of part representation that's created with a linear finite element techniques, and then that flexible part is brought into Atoms for incorporating into a dynamic analysis, so that you can actually calculate time-varying deformation and stress within an Atom simulation. To do this, it requires, a minimum requires an Atom's Flex license. So that includes both solver components and user interface components. And also an Atom's Durability license is required to recover stresses in atoms. So the basic Flex license just gives deformations. Now these flexible bodies, like I briefly mentioned, uses a modal approximation technique, which greatly reduces the number of degrees of freedom. But because it is a modal formulation, it's based on linear theory. So these flex bodies are really only valid for fairly small deformations on the order of about 10%. In fact, if you get deformations in your Atoms model exceeding that, you'll likely get a warning saying, hey, you're probably exceeding the linear assumption. So this is my one-page slide here on Atoms Flex theory, but I think it's kind of good to just know this basic information here. If you think about a finite element model, and let's say a finite element model has 10,000 degrees of freedom, well then in theory it's going to have 10,000 natural frequencies and 10,000 mode shapes associated with those natural frequencies. So if you look at like a beam example, a simple beam, here pinned at both ends, here's its first mode of vibration with a certain natural frequency, and here's its second mode with a certain natural frequency. So these nodal deformations are called mode shapes, and so here's the first mode shape, and here is the second mode shape, on and on and on until you reach the end. So in Atoms, we don't carry all the mode shapes because that would be too intensive, and usually the higher frequency modes aren't that important anyway. So we carry a certain subset of those modes, and those are represented by these columns of phi here. Now there's also these, so really what we do, I guess, in Atoms is we form a solution that's a superposition of these fixed mode shapes. And so we have these scale factors here, which I probably should have used a different symbol in phi since I've already got it here. But these scale factors are time-varying scale factors. And so you have scale factors on these mode shapes, and those basically determine the final solution. So what Atoms does is it calculates these time-varying scale factors on the mode shapes. Everything else, the mode shapes and the natural frequencies, those are calculated by the finite element code. And the finite element code then writes out a modal neutral file. It's called an MNF file. And it includes all the natural frequencies, these lambdas here, as well as the modes, these column vectors phi. Okay, so why do we use this approach? Well, the reason is just computational efficiency. You know, if you think about it, if you had a 10,000 degree of freedom model and then you reduce that down, you say, okay, I'm only going to carry 20 modes in this modal approach. Well, you've decreased the number of degrees of freedom that you need to solve for dynamically from 10,000 down to 20. So it's a huge savings. The only disadvantage is you kind of have to worry about the modes that you've truncated, whether or not those have effect on your solution or not. Okay, so like I mentioned, the FAA program does the modal analysis, writes that out to a modal neutral file, and that's what you import into Atoms as the flexible body representation. So now I'm just going to talk briefly about the product. So Atoms Flex is the basic one. That allows you to calculate any time-varying deformation, nodal deformation. And we support most of the major commercial finite element codes out here, which you'll see listed. And really the benefit of this is to help you really capture compliance effects in your Atoms model so that you can predict loads with greater accuracy. Now we have an additional module called Atoms Durability, which is kind of a prerequisite for this is Atoms Flex. And what this does is it allows you to calculate time-varying stress as well as deformation. So what we do in that case is we just include stress mode shapes from the finite element model. Those get written into the modal neutral file as well. And so that can be really helpful for calculating stress margins. And also we have a kind of a nice link from Atoms to our MSC Fatigue program so that you could basically take a time history of stress in your Atoms model and export that out to a fatigue program like MSC Fatigue to calculate fatigue damage. ViewFlex is a relatively new tool that came out about 2 years ago, and this allows you to create flexible bodies completely within Atoms View or Atoms Car. So you don't need any external finite element program at all. What we do is we have a part of Nastran embedded inside of Atoms. And it's very quick and easy if you just want to quickly create a flex body. It's a great way to do it. You don't have quite as much control as you would if you were working in the finite element program. For example, I think ViewFlex you can only use 10 elements, where if you're in Patran you could mesh with brick elements or whatever you wanted to do. So that's a powerful tool. Hopefully we'll have time to go through that briefly at the end. Here's just one case study I thought we would present. This was John Deere. They used Atoms and to really model the load history and fatigue associated with the machine you see here. As you can see in the video, it's going under a lot of deflection and stress and load. And this is a perfect application of using Atoms Flex. And of course, they were able to really reduce their time to market and got the number of prototypes down to 1. So this is just one sample use case. We have a whole bunch of them, but just kind of give you an idea how something like this might be used. So a question comes up is, if I'm using this modal approach, how many mode shapes do I need to carry? And it's kind of a tough question to answer. It depends. There's a lot of engineering judgment involved. But a general rule is that you probably want to carry modes up to at least 2 to 3 times the frequency at which you're going to excite the structure. But there's another measure that a lot of FEA guys use called modal effective mass. And what that does is it calculates the mode-by-mode contribution of each mode to each rigid body motion in the X, Y, Z, and rotation X, rotation Y, rotation Z. And theoretically, if you had all the modes, you would get a modal effective mass of 100% in each direction. You'd have the total mass of the part come out to be whatever its mass is in each of the 6 directions. But with modal effects, truncation, it's going to be less than that, and some people recommend, use 80% or make sure you have 90% or more of the total part mass. You can do that by using this modal effective mass command inside of the Nastran input file. If you do that, I'd first encourage you to take a look at the Nastran Quick Reference Guide to really kind of understand what this does and some of the nuances of this command. But it is useful. Okay, so in this demonstration problem, we've got a simple 4-bar mechanism here, like modeling a single-cylinder engine, where the crankshaft's being rotated at 12,000 degrees per second, and we want to make the connecting rod here flexible and kind of look at how much it deforms during operation. I'll talk about the damping a little bit later. Let's just go to the actual demo now. So here's the Adams view model, and I could just show you a simple animation of this. Okay, so here's the part going through its motion. Now, to make this part flexible in an external fine element code, first thing you got to do is export the geometry. Okay, so you can do that through File, Export, and then just pick, Parasolid, and then give it a file name, and it will write it out to a Parasolid file. And then you can read that into Patran. So I've already done that here. I've read that into Patran. When I did that, the piston came in and the crank came in as well, but I just deleted those to save a little time. And also to save a little time, I created nodes at the center of the holes, which we're going to use for the attachment points. So I've got this geometry in here with a couple nodes. And the first step is to mesh the part. So I go to the Meshing tab in Patran, and I create a solid mesh. And I pick the Tet Mesh. I'm going to use a Tet Mesh with 10 elements. You go to Tet Mesh Parameters, and you've got some control over some of this features. The one thing I like to change a little bit is the curvature check. So you can specify this H over L distance that you see here, this ratio. So the smaller the number you put in there, the more elements you get in a curve region. So I'll set that to 0.05. The automatic calculation for edge length, I'm going to set that to 0.18 inches. Then I have to pick the part I want to mesh, so I come over here and I pick the solid. And now I'm ready to mesh it, so I just hit Apply. And Patran goes through and meshes the part. I can toggle between the node and size up here, and also the point size here. Okay, so I've got this part meshed. Now I want to specify some material properties, so I would go to Properties, Isotropic. We'll create an isotropic material, and we'll give it a name like steel, for example. And then we'll specify modulus, so like 30 e to the 6, 0.3 for Poisson ratio, and a density of 0.283 pounds per cubic inch. And we'll talk about these units a little bit later. It is important. Okay, so we'll say OK to that. Hit Apply and create the material. And then now I need to create a solid property definition. So I'll for lack of a better name, I'll just call it solid. And for the inputs, it's a solid element, so I only really need the material. I'll pick a steel there. Now, if you had shell elements or beam elements, there's more information, obviously, like thickness and things like that you'd have to put in here. And then the application region, again, is going to be the solid, so we'll add that, say OK. And then finally Apply. That creates the solid property. So now I've got the steel meshed beam, and before I can run the analysis, I have to specify what are called the attachment degrees of freedom. So remember, in the Adams model, this beam, or this link, was attached at each end through a marker. Okay, and so we need to have nodes where those markers are in the atoms model, and that's why I created those nodes at the center. The other thing we have to do is, since those are idealized joints inside of atoms at a location, at a marker, we need to transmit the load from all these finite elements down to that single node. And the way we can do that is with rigid body elements. And Patran has a new utility that's kind of useful for that. You can go to Tools, Utilities, FEM, General, and you'll see this one down here called RBE2, RBE3 Spider. You click that. You have your choice between RBE2 or RBE3. RBE2s are perfectly rigid elements. RBE3s have a little compliance to them. So it's kind of up to the engineer which he thinks is more applicable. But these are bar elements that are going to spider down from these elements to this one center node. So normally you want to pick all 6 degrees of freedom. Doesn't really matter on solid elements since you have 3 degrees of freedom. But if you were using shell or beams, definitely you'd have 6. And then I don't want to exclude the mid-side nodes. I want to include those. This auto execute button is there. If it's checked, it will automatically execute the command as soon as you enter the information. It's a little scary for me. I usually turn it off because I don't really want to hit the apply button until I'm sure I got everything right. And then there's this auto create reference node. So I could have the utility automatically create a node at the center. The reason I'm not doing that is because there's a little bit of round-off error in the calculation when it does that, a couple of thousandths of an inch. And that might be enough to issue some warnings in atoms when you convert those back to the markers. So I want it right on the money, so I created it myself. And so now you just have to pick a reference node. That's going to be node 1, which is at the center here. And then I pick the location right there. And I pick a surface from which to spider to, so I'll pick that surface there. And then I can just hit apply, and it's going to ask me, are you sure you want to do that? And I say yes. And you can see that now it goes and it creates these rigid body elements that spider back to the center node. Okay, so now I'm just going to go repeat that for the other end. Okay, so I do the same thing. Set this to node 2 this time. A new point, new surface. So the node is again at the center, and the surface is right here. Hit apply. Yes, and it creates the rigid body elements. Okay, so now this thing's almost ready to run. There's one more step we have to do. So remember these 2 attachment nodes. These are the real important nodes because they don't get converted into modal space like everything else. They're physical degrees of freedom. And we need to specify that what those attachment points are going to be in the modal neutral file. And the way we do that is through the loads and boundary conditions. Let's see, meshing. Say create degree of freedom list, and you pick the nodes. Well, let's first give it a name. So I'll call this my DOF, for example. And we'll define the terms. So we're going to use nodes 1 and 2. And we're going to specify all 6 degrees of freedom. And hit apply. Okay. Notice I didn't, I'm ready to run this model now. Notice I didn't create any boundary conditions, hard boundary conditions to fix those nodes like you would maybe in if you were just running a modal analysis. What we're doing here is a little bit different. We're really creating a super element inside of Patran. So we do that by just using this DOF list to specify those attachment nodes rather than using the boundary condition tab. Okay, so now we go to analysis and an analyze entire model full run. First thing you want to do is pick the solution type. We're not going to use linear static here. We're going to use normal modes. Make sure you select those A set degrees of freedom. Then we go to solution parameters. Now this is very important, this weight-mass conversion factor. Remember, I entered my density in pound mass per cubic inch. And that's not really a consistent unit because 1 pound mass times 1 inch per second squared does not equal 1 pound force. In fact, it equals 1 over 386 of a pound. So I have to put in that factor here. If you're just using kilograms, newtons, and meters, something consistent, you don't have to worry about this. So you set that, and then you go to Adams preparation and change this from full run to modal neutral file. And if you're using another finite element program, it's probably got something similar to this, hopefully. Check the units, make sure those are what you're expecting. And we're going to specify 26 modes, so we don't need to put any upper or lower bounds. Notice this mass option here. What does this mean? Well, there's a couple ways Adams can create the, Nastran can create the mass matrix. If you use full, that's the most accurate. And if you pick full here, you can always go into Adams later and reduce it down to partial, and it'll take out those extra terms in the mass matrix. So let's just go with full for now. Hit OK. It's just saying I got nothing in these lower and upper bounds, so you can just say OK to that. Okay. And then we hit OK. Hit OK once more here. Then we go to subcases, and we take a look at that default subcase that gets created. And we go into subcase parameters. And here the really only thing you need to do, remember before we specify the number of modes that we're getting written out to the modal neutral file. But what we need to do here is tell the Nastran how many total modes to calculate, so we can change that to 26 and say OK to that. The only other thing, output requests, okay? So if you want to be able to calculate stress in Adams, you have to come into here and pick grid point stresses and add that as well. And also, of course, you have to, oops, I picked the wrong one, didn't I? I want grid point stress. And if you also, of course, you have to have the Adams durability license. Okay. And then hit apply and cancel. It's kind of a delay here. I'm not sure why, but yes there. And then after that's done, I go into subcase select and just make sure that you have the right subcase selected. And then you're ready to run the analysis. So really all you got to do then is go down and hit the apply button at the bottom of the form. And what that will do is it will run the modal analysis, and it will create the modal neutral file. Okay, and then once that's done, you can go back into your Adams model now, and you can just right-click on that part and say, make flexible, import an M&F, and I'll pick the M&F that just got created. Now there's a couple different ways to align the Flexbody. Normally, if you did it the way I did it, everything should work just perfectly. It should come back right where it started. Because when you export the part file, its coordinate system should be the same when you bring it into Patran. Okay? You can see the meshed part there. But there are some techniques to move the M&F file around if you need to, like aligning it with the center of mass of the part. So there's a lot of information here I won't really be going into, but it's in the online help. And then connections, okay? So this shows you the joints and forces attached to that part, the markers that they're at, and what nodes they're getting converted over to. So these are getting converted over to nodes 1 and 2. You can see that all these are zeros, so everything's coming in at the right place. The center mass is off a little bit in the finite element calculation from what Adam's calculated, but that's okay. And then we hit OK there. And so now I've got this flexible part in Atoms, and it's ready to run, actually. But let's just create a measure real quick. I'll go to Design and Exploration and create a point-to-point measure. And we'll go from attachment node 1. How do you know which is the attachment node? Well, if it says interior, that means interior node. That tells you that it's an attachment node. Click OK. Oops, wrong one. Marker, pick. And then we go down and do the same thing. Or you can just say guesses and it'll probably show up. Yeah, right there. Changes to magnitude, hit OK. So what we're going to measure now is the distance between these two attachment nodes. Okay, so if I ran a simulation now, okay, the model runs. Yeah, you get this warning down here if you're using solid elements. Notice what it says. It says the flex blah 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 attachment node has 0 rotational mode shapes. Well, that's to be expected for solid elements, so it's kind of an innocuous message because solid elements really only have 3 degrees of freedom. Okay, and so here is a plot basically of the end-to-end distance between those two pinholes. So you can see you're getting a little bit of stretch there as the part undergoes the inertial loading. Another thing you can do, if you go to Results, Post-Processor, you can load the animation. And if you had MSC Fit, if you had a license for durability, then you could go into contour plots here and pick stress and look at different stress throughout the part. Okay, so that's something else you can do if you have that license. Okay, let's see how we're doing on time here. So I think I have time to do, it's 10:30, yeah, okay. So I think I got time to talk a little bit about ViewFlex. So let's just close out of this for a moment. And I'm going to open up a model again. I'm going to open up basically a new version of the model. Okay. So if you have the ViewFlex option, like I mentioned, that makes it so you don't need to use an external finite element program. You can just right-click on the part, say Make Flexible, and this time, instead of saying Import M&F, say Create New. And now this will bring up the ViewFlex form, and you can just say number of modes, you know, like 26 or whatever. Tell if you want to do stress analysis to calculate the stress mode shapes. And I usually go to advanced setting so I can play around with some of the meshing things, like you probably don't want linear elements, you probably want quadratic elements. And you probably want to be able to custom change the size of the elements, the average element size, like that, for example. And then it'll go through and it'll create a mesh. Now, the meshing takes a little bit longer here than it does in Patran. Not sure exactly what the reason for that is, but once the meshing is done, you can see here now that it's created a mesh I can look at. Now, I really haven't created the Flexbody yet. It's just created a mesh. And it's asking me temporarily, saying, hey, do you want to keep this mesh? And if I do want to keep that mesh, then I'm ready to go over to the Attachments tab, say Find Attachments, and it finds these two attachment nodes, right? And now here's where it gets a little interesting. You have some choices on how you want to connect up that connect that node up. So if you want to do it the same way I did in FEA, then you'd want to change this to cylindrical. So you're basically going to spider out to a cylinder, and you'd pick a radius. So my radius was 0.2. So I'll go a little bit bigger than that just to make sure I capture everything. And then you have to pick, okay, now let's go zoom in a little bit first. Okay. So what I want to do now is I got a marker here called reference to. I'm just going to make a copy of that, and you'll see why in a second. So I'll say copy, and then I'll modify it. And I just want to move it out in the Z direction a little bit. Okay, so there it is. Now, the reason I did that is so when I go up to here and I put in that dimension again. Okay, and now if I pick on, let's do this one first. Okay, so that's actually at the other end. Well, let's do this one first. Okay, so now what I do is I pick the reference coordinate system from where to spider out. I go pick coordinate reference here, and I pick that marker, and then I pick I'm sorry, got this back again, 0.205 inches, and then pick the end location. So that's why I created that other marker out here, so I could have a vector to point to. Right there. Okay, now see that little cylinder there? That's going to be my RBE surface, my cylinder surface. So then I could say transfer IDs. And now I'd have to go back and do the same thing for the other side. And then I'd hit apply, and it would create the flexible body. So I'm going to skip those steps because I'm really kind of running short on time. But really all you got to do is just go to the other end, do exactly what I did to the other end, then hit apply, and it will create the complete flexible body with the RBE elements. Okay? So let's I think we're done with the demo part now, and I'll go back to the PowerPoint briefly. A couple more things to talk about. One is this damping. So in atoms, since this is a mode representation, you do have control over the damping ratio for all the different mode shapes. And by default, they're not 0. Atoms has these values. So it depends on the frequency range of the modes. How do you know what the modes are? Well, I can show you that in just 1 second. I will do that right after this slide. One thing I want to get across from the point to get across, though, is you can also bring in a damping from your FEM model. If you had like generalized displacement-based damping, it's possible to bring that in as well. The last thing I kind of forgot to show you here, if you have a flexible model like this one, you can always right-click on it and say modify, and now you can step through the different modes. Actually, I don't have an MNF for this one, I don't think. Okay, so you can step through the different modes and see what their frequencies are, and you can enable and disable modes based on frequency. You can even animate the modes. I kind of forgot to mention that before. Okay, so a couple other things. Modal forces. So what if you want to apply a distributed load to one of your flexible bodies? Well, the way you do that is through this modal force option. And really what you have to do is in the finite element program, you have to create a load case like a pressure over a surface and define that as a static load case. And then if you've done that, you can actually get the modal force included in the modal neutral file so that you can model the distributed body. You can also, there's other ways you can create modal forces. It can get kind of complicated. If you look in the user guide, the online help, you'll find all the different ways you can do it. But just remember that if you want to create a distributed load on a body, this is the tool you use, the modal force. And generally, you're going to have to create those load cases in your finite element program. You can do those either through a function, a subroutine, or a force. Here's an example where I took that connecting rod and I put a distributed load across it. You can see it deform here in atoms. That's an example of a modal force. It's also possible to add a preload to a body. Like maybe I want this thing preloaded. If you do that, it's kind of a two-step operation. You have to go into Patran and Nastran and do the first run to calculate the initial preload case, then run the modal analysis on that pre-stressed body. But it can be done. The only thing you got to keep in mind, though, is you cannot scale a preload. So if this thing's preloaded, the preload is what it is. You can't scale it up or down inside of atoms. And the other thing, too, is it will actually try to recoil if you bring it into atoms because it's preloaded. But sometimes that can be of use. Last comment, not all modal neutral files are created equally. If you use Nastran, you can see that all these different features are supported. For example, stress modes, preloads, residual vectors. We really didn't talk about that, but that's just another way to kind of compensate for modal truncation. Whereas some of these other codes don't support those various features, so just keep that in mind as well. But most all of them support the basic functionality. Okay, so in summary, you can bring these finite element bodies into atoms with Atoms Flex. You can get finite element stresses in atoms using, it should say atoms durability, apologize for that. And you can create flexible bodies solely within atoms using the Atoms View Flex tool. So the bottom line is really if you do this, hopefully you can add a lot of realism to your model, help you evaluate those nagging compliance effects, and help you evaluate the robustness and reliability of the product as well. Okay, so I think that's all for my presentation. I'll pass it over to Yijin now.